Okay, in this video I'm going to try and show you how to actually calculate a half-range Fourier series expansion. And this is actually going to continue the same example we saw in the Desmos graph. So I'm going to start with f of x is x squared from 0 to 2, and I'm going to try and find a cosine series. Okay, so right off the bat, I see that it's going from 0 to 2, and it's supposed to be a cosine series, which means secretly we're going to be going from negative 2 to 2, which means that our p is equal to 2. So finding your p is super important. Make sure you're finding it correctly. Cosine series, we're secretly looking at negative 2 to 2, so p is 2. Okay, so we have formulas. A0 is 2 over p, integral from 0 to p, f of x dx, which means we're going to integrate 2 over 2, integral from 0 to 2, x squared dx. Integral of x squared is 1/3 x cubed, so we have 1/3 x cubed from 0 to 2, which is 8/3. Okay. An is 2 over p, definite integral from 0 to p, f of x times the cosine of n pi x over p dx. P is equal to 2, so we have 2 over 2, integral from 0 to 2, f of x is x squared, cosine n pi x over 2. Okay, and then this integral looks an awful lot like it's supposed to be integration by parts. And movie magic tells us that it's equal to 16 negative 1 to the n divided by n squared pi squared. Okay, so then we plug that into our Fourier series. F of x is equal to a0 over 2 plus the sum, n equals 1 to infinity, an cosine n pi x over p. We don't need signs because we're finding a cosine series. So a0 is 8/3. We divide that by 2, and then plus sum, n equals 1 to infinity, an, which is this fraction we found for the previous integral, and so we get some kind of answer. And maybe there's some simplification that can happen, but I'll just leave it at that for now. Okay. Next up, I want to do the same example, only using a sine series. So again, sine series means we're integrating from negative 2 to 2, and it means that p is equal to 2. And so we have a formula for a sine series, which is bn is 2 over p, integral from 0 to p, f of x sine n pi x over p dx, which is 2 over 2, integral from 0 to 2 of x squared sine of n pi x over 2 dx, which again is looking like integration by parts twice, and that should turn into 8 times negative 1 to the n plus 1 over n pi plus 16 over n cubed pi cubed times alternating sign minus 1. Again, remember alternating signs typically are coming from cosine of n pi's. Okay, once we have our formula for bn, we just write our answer, which is only the sine part of the Fourier series. We don't need to worry about an and a0. We just have bn times sine n pi x over p. Okay, so for us, that's going to be n equals 1 to infinity. Copy down this gigantic mess. Oops. And multiply by a sine. Okay, so that's the answer for a sine series. Okay, just a reminder for both the cosine series and the sine series, we're doubling our integral and switching it to go from 0 to p instead of going from minus p to positive p. Okay, finally, I want to try and find the Fourier series of f of x is x squared from 0 to 2. So this is our half-range Fourier series. So from 0 to 2, that means that our p is essentially going to end up being 1. And so if I go back to our previous formulas, or our formulas for the half-range series, what we end up seeing is that we have a 1 over p, and it should be integrating from -1 to 1, but we're going to say those two are equivalent, so we'll go from 0 to 2, which is actually 2p f of x dx, which is an integral 1 over 2, integral from, p is 1. It's so easy to mix up your 2's in this example, in this problem, the half-range Fourier series. So p is 1, which is 0 to 2, f of x is x squared dx. That's what I should be seeing is the integral of x squared. The 2's are going to kill me every time, though, if I'm not super careful. So making sure I'm plugging in p is equal to 1, I get 1 over 1 integral from 0 to 2 of x squared, which is going to be 1/3 x cubed from 0 to 2, which is 8/3 again. Okay. An is going to be 1 over p, integral from 0 to 2p, f of x times the cosine n pi x over p. If you're looking at this in the book has it written a little bit differently because they use the number L here, and so this would be half of L and this would be half of L, but I'm going to use p. Okay, so let's see, p is equal to 1, so we have 1 over 1, integral from 0 to 2, f of x is x squared, and we have cosine n pi x over 1 dx. So it's a little easier to integrate. Okay, so I'm going to put ... and write the answer. Okay, so our answer is L squared over n squared pi squared. One downside about the Fourier series, the half-range Fourier series, is typically it's not going to be even or odd, and so we are going to have to find all three. Okay, so Bn is the same as An, only with a sine instead of a cosine. Okay, so we have 1 over 1, integral from 0 to 2, x squared sine n pi x over 1 dx, which again, all of these integrals end up being integration by parts other than the really simple a zeros. So I'm going to pause and write down an answer. Okay, after integrating, you should get minus L squared over n pi. And so all that's left is to combine a0, an, bn into our Fourier series. So f of x, as always, is going to be a0 over 2 plus a sum from n equals 1 to infinity, an cosine n pi x over p plus bn sine n pi x over p. Okay, so a0 was 8/3. We divided by 2 plus a summation. An is L squared over n squared pi squared. And p is 1, so that's really just going to be cosine n pi x. Plus bn, should probably have just written minus L squared over n pi. And we have sine of n pi x. Okay, and so that's our answer for the half-range Fourier series expansion.